Here is a very special surface that we have before us, the Mobius Band or the Mobius Strip. Now, before we go actually to the Mobius Strip and what is so special about it or so interesting about it, we know that if we want to have a cylinder, what we have to do is take a strip of paper, join the two ends, the upper end with the upper and the lower with the lower, and you get a cylinder. This is almost like that but slightly different. You take a strip of paper, but instead of taking the upper with the upper end, you twist, just one twist, and then attach the ends. So I have taken once again I'll show. It is called a half twist. We take a half twist and then we glue it up. Now I'm taking a sellotape and going to glue it up. And this is what we have. It's different from the cylinder. Now we can make this with a paper. It's very simple to make. But the properties that I want to show you, I will not show on the paper because paper can get torn off. As you can see, this is a very similar one. And I have it in two colors, so you can see that because of the twist, the red and green, the red and red will not meet, but the red and green will meet. So this is the Mobius Band. We took a strip with red and green sides, gave a half a twist and stapled them together. Now what is so special about this? It has two very special properties. Now if you take a point here, say this one, then just behind it there is the point. It is a point on the same surface, and we normally call this as one side of the surface and this as the other side of the surface, and the two sides are separated by a border. For example, the sphere also has two sides, but there is one that is outside and one that is inside, and it has no border, no edge. You cannot go from outside to inside because there is no border, no edge, and you remain always outside or always inside. The same thing happens with the cylinder. You start with one point, go all the way around and come back to the same place on the same side. Now in the sphere we talked about the opposite side. In the cylinder, if you want to go on the opposite side, you have to cross the edge. Let us see what happens here. See, I am taking a point here. Now this is one side and this is the other side. I want to reach here, which I have marked here, the other side, and our normal assumption would be that we will have to cross the border either here or somewhere here. Okay, let us see now. See, I am going along this dotted line. And I have reached this point which we had marked. We had started with the red point here and we had marked the green. On the green we had marked the point on the opposite side. We reached from here to there without crossing the border. You can try it, it's very interesting. And because you have not crossed the border, you are on the same side. And therefore, this Mobius band is supposed to be a surface with only one side or a one-sided surface. That's very special property. Very few surfaces have this property. Now there is another very special property which this surface has, and that is orientation. That means you start at a point, you see this. I don't know if you can see it. This is a thumbtack with the head at the bottom and the pin at the top. Now what we are going to do is, we are going to start with a point here on the surface. We can take the same point. And I will keep the head below and the pin above and let it move on the surface till it comes on the opposite side. Let us see now. See, I am still going without crossing any border on the same side. We just saw, I will repeat that part again. We just saw that if we take a thumbtack with the head at the bottom and the pin at the top and start moving, now you can see that I am moving on the red line, on the red side rather, from this point. And we are going in a straight line along the same side, and as you can see I have the head in my hand and the pin is at the pointing upwards. We have finished this once. I am just repeating in case we have not seen it properly, and we go till we come back to the same point where we started. Now here is the point where we started. Now if you recall, look at the direction of the pin. The pin is here. Actually, if you look at it here, at this point the pin has changed its direction. Originally we had started with the pin like this. The pin was like this. And we ended up with the pin in the opposite direction. And that is why the whole orientation has changed. The upwards has become downwards, and therefore it is called a non-orientable surface. These are two very special properties of the Mobius band. We saw already that Mobius band or Mobius strip is a very strange surface with very strange properties, strange in the sense that not many surfaces have these properties. There is one more strange thing about this Mobius strips, and that is this. Suppose I take a cylinder and now I cut it along the central line parallel to the edge or to the base. I will get two cylinders again of half the height and same radius of the base. What happens if I cut it at the trisection points? That means like this. One cut like this and another cut like this. I will get three cylinders with 1/3 the height and the same radius for the base. Okay, that seems to be very natural and very obvious. What happens in case of a Mobius band? Now, here we have a Mobius band, and I have marked the point halfway between the two edges. In this Mobius band, I have marked 2 points giving me 1/3, 1/3 and 1/3. What we will do is, like we were talking about the cylinder, we will try to cut this. I am cutting it along this point which I have marked. I have put a small cut, and now I will continue cutting all the way parallel to the edge. Now you know that this has only one edge and one side. So when I go parallel to this edge, I will also go parallel to the other edge, and ultimately when the whole cutting is done, we would expect that we should have two Mobius strips. No, we have only one strip. after the whole cutting. I have not cut here just to save time, but this is the way we cut it. And after the entire cutting is done, we will go like this. We will go all the way along my finger and come back to the same point. So this will give us one, but this is not a Mobius band, it is not a cylinder, it is a band or strip with two twists. Okay, now we will not say that there will be three in here, because we know that this is behaving very strangely and differently. Alright, what we do now is same thing again. I will mark the 3 points. I start cutting along one. This is now 1/3 the width and parallel to one edge. We'll continue like this. And I will not cut the whole thing, but you will see that I will go along my thumb close to this 1/3, 1/3. I'll show it like this. 1/3, 1/3 is here. 1/3, 1/3. Oh, I've reached this second point. We started with this point and I have reached the second 1/3 point, and that means that when I go all the way around, I will come back here. So just in one cut, I will not have to make two cuts now as in case of cylinder. I will have to make only one cut and it will cut the entire Mobius strip. And what shall we get when we ultimately go all the way around and come back to this point here where we had started? We will get this. There will be two interlocking twisted loops. Now, this is a little strange and we are not going to explain it. We are just going to practically see that this is what happens. What you can do is, you can make Mobius bands and try to cut them like this, make them out of paper. If you want to make the two sides obviously different, what you can do is, before pasting the two ends, on one side you can just draw oblique lines or squares or something, or stick another paper, so that when you join you can see the two colors differently as you see here. And then try to cut and see what happens, how exactly it happens, and so on. So we hope that with this very nice looking thing, a very nice surface in mathematics, the Mobius strip, we can have a lot of fun. I hope you will have a lot of fun mathematically and practically.